In this video, we are going to consider least squares problem. And the idea is that you might have this vector equation, ax equals b, that is inconsistent, but you still want to find an x that gives us the closest solution. In other words, an x that makes our b minus ax as small as possible. This is our overview slide here with all the main points. We'll spend a few minutes on this slide before going through each point in more detail and with more examples. To define the solution of our least squares problem, we have if A is an m by n matrix and B is an Rn, a least squares solution to the equation ax equals b is an x in Rn such that the distance between b and ax, or that is the distance b minus ax, is less than or equal to b minus ax prime for all other x prime in Rn. So in other words, it's the x that minimizes b minus ax. We also want to notice, since ax is in the column space of A, right, because ax is a linear combination of the columns of A, so it's in the column space of A, we are seeking an x that makes ax the closest point in the column space of A to B. We use this theorem here, which gives us the normal equations for ax equals b. And this theorem says the least squared solutions of ax equals b coincides with the non-empty set of solutions. By non-empty, we mean that there's always a solution of the normal equation A transpose ax equals A transpose b. So what we do, or what this theorem allows us to do, is convert from this ax equals b equation, which may or may not have solution, to this normal equation, A transpose ax equals A transpose b, which always has solutions. And if you think about it, we'll always have solutions if we're looking for a least squares approximation. You know, we can always approximate a solution, and we can always then find the one with the least amount of error. And the other thing I want to mention is I don't believe your book puts the little hats here, but I put that to emphasize the fact that this x is different from our original equation, and this b here is different from our original equation as well. Before we briefly overview how we derive this normal equation, we'll do an example to show how we can solve or how we can do a least squares solution to the inconsistent system ax equals b, where A is the 3 by 2 matrix with column vectors 4, 0, 1, 0, 2, 1, and B is the column vector 2, 0, 1. So first, we need to find A transpose A. So this is what I have here. I have A transpose here times A, and that gives us the 2 by 2 matrix with column vector 17, 1, 1, 5. Next, on the other side of the equation, I have A transpose B. So here I have A transpose times B, which gives us the column vector 19, 11. So now I've transformed my original equation to this equation here, the normal equation. A transpose AX equals A transpose B. That's what I have here. A transpose AX is equal to A transpose B. And I can solve this here. I mean, we know how to solve the system of linear equations. We can do row reduction, but I went ahead and did this using the inverse. So I have then my x hat now is equal to my vector 1, 2. And x hat here is my least squared solution. We will spend some time in our regular video deriving the normal equations for ax equals b, but here is the overview. First is to note that ax is in the column space of A, because essentially what ax is doing is x is a weight for each of the column vectors of A, so it's essentially a linear combination of A. Therefore, if b is equal to ax, that means the b that's associated with the least squared solution is in the column space of A. Next, we're going to use the best approximation theorem from chapter 6.3 about orthogonal projections to determine the solution of the least squared problems is the orthogonal projection of B onto the column space of A. So remember, we can't reach B using AX. This is not solvable, but the the solution for our least squared solution, if we're looking for something that ax can equal to, that's some b in the column space of A. So we're going to use the projection of B, the one that comes with our original solution, so our equation, ax equals b, and as close as we can get will be the orthogonal projection of B onto the column space of A. Next, we're going to note for the least squares problem, then we are looking for x hat that satisfies ax hat equals b hat, where b hat is the projection of B onto the column space of A, this b hat here. Then we're going to use the orthogonal decomposition theorem to find a vector z orthogonal to b hat. And from this chapter here, also 6.3, we found that z is equal to b minus b hat. And that means that z is orthogonal to the column space of A, and therefore any column vector of A, such as A sub I, is orthogonal to z. So z equals b minus b hat, which is equal to substituting our ax hat for b. Remember, we did that here. That means A sub I dotted with b minus ax hat should equal to 0. And since this is true for every column, we can then take, remember the dot product, if we want to convert it to a multiplication, gets to be a transpose. So we can take this, and that's A transpose, the matrix A transpose, times b minus ax hat should equal to 0. And this gives us the information to solve for x hat is equal to A transpose A inverse times A transpose B. So this is the overview. And I'm going to say, if you look at this, a lot of the individual steps, like step 1, step 2, step 3, and step 4, or actually not step 3, but 1, 2, and 4, are all things we have learned previously. Step 3 is just a small note, and step 5 is just some algebra. This theorem here gives us criteria for unique least squared solution. Remember, there's always a set of solutions, and in fact, when there is a free variable, there's an infinite number of solutions. So this tells us when we will have exactly one solution. Let A be an m by n matrix, then the following statements are logically equivalent. 1, the equation AXB has unique least squared solution for each B and Rn. 2, the columns of A are linearly independent. 3, the matrix A transpose A is invertible, and when these statements are true, the least squared solution x hat is given by x hat is equal to A transpose A inverse, A transpose B. And that wraps up our overview. So now we can go over each topic in more detail, especially this derivation, and with more examples for everything. I have copied these 3 main points from our overview slide. First, sort of the introduction to the least squared problems that were given this matrix equation ax equals b that's possibly inconsistent, and we want to find an x that comes as close as possible to solving this equation. And from that, we have defined the least squared solution, that it's going to be this x hat, such that b, that would be the actual vector we're trying to reach, b minus ax hat is the magnitude of this is minimized. It's the smallest, so there's no other x in Rn that could have a smaller value. So that x hat would be our solution. And then we had this theorem which gave us a way of calculating x hat, which started by saying, well, if we have ax equals b, then we can do A transpose on both sides, and this will lead us to a solution. So what we are going to do next is kind of look at how we get from this definition of the least squared solution to this theorem that tells us the equation of how to solve it. So kind of some intuition behind these two things. So I've started with this drawing. The idea is you have some space over here in Rn that you have vectors x. I should put a little vector sign on that. And then you have this matrix that transforms x into another subspace of Rn, and actually it's worth noting that that subspace is the column space of A. I'm going to write that down. So Ax is in the column space of A, so once we transform over, we're in the column space of A, that's the subspace of Rn. And just to remind you, because it's been a while, this is from chapter, I don't know, 1 or 2. So AX, that's if we have the matrix AX and the column vectors are A1, A2, and AN times X, that's going to give us x1 times the first column vector, x2 times the second column vector, all the way to xn times the nth column vector. So here we can see that AX then is a linear combination of the columns of the matrix A, hence in the column space. Also, again, because it's been a while, if you don't remember how this AX translates to this linear equation, I've written it out in painful detail. So here's my matrix A with the first row, second row up to the nth row. Here's my xn. I do my row times column multiplication, row times column multiplication to get this matrix here. But now I can separate this out as, separate out each addition portion. So this is one vector, the A1 x1, A2 x1 up to AM x1, and I separate it out as A1 A2 AM1 times x1. I separated out this vector here, and then etc. up to the last vector. So that's what gives us the linear combination of the column vectors of A. So I know it's been a while, which is why I thought maybe we could refresh that, but I'll also say since we're coming to the end of the term, it's this is stuff you want to make sure is fresh in your mind as we come towards finals. Okay, so now we've established when we map X by multiplying times A, we get mapped over to the column space of A, and so we have this B vector that I should put a little vector sign on that. So we have this vector B that we get mapped to. And actually, not to confuse that, actually this is confusing, but we have this other B here. Maybe I'll write it in blue just to emphasize this is a different B that we are given. And we're asked, okay, when we have this equation here, we're asking, how do we find an X that maps to this blue B? And the answer is, well, since A maps to this subspace here, there's no X over here that will map to this blue B, because this blue B is not in the column space of A. So what we want to find is this vector B here in the column space that is closest to this blue B. And from our last video, we have this best approximation theorem that said let W be a subspace of Rn. In this case, our W is this column space of A, and let Y be any vector in Rn. In this case, this blue B is our Y. Then Y hat be the orthogonal projection of Y onto W. Then the Y hat is the closest point in W to Y. So what this is telling us is the vector B here in the column space of A that is closest to this blue B is the orthogonal projection of this blue B onto the column space of A. So I rewrote this theorem in terms of, instead of writing W, I put the column space of A. Instead of Y, I put B, just because I got tired of translating. But also that means we should make this vector B and this vector here B hat. So now I'm going to say by my best approximation theorem, if we have the column space of A is a subspace of Rn, and B is a vector in Rn over here, and B hat is the orthogonal projection of B onto the column space of A, then B hat is the closest space in the column space of A to B, in the sense that it's the thing that's closest, the smallest distance. So I've written this down, that the B hat over here that we're looking for is the projection of B onto the column space of A. And I also have this, I've done this line here in the right angle to remind us that B hat is the projection of B onto the column space of A. Also, this is projection of B onto the column space of A. This is not the cola or something. I'm going to make one more notation on my graph based on the orthogonal decomposition theorem, also from our previous video. So and again, we're in W's and Y's, but you'll have to, I guess, put up with it for now. So let W be a subspace of Rn. Again, we're talking about the column space of A. Then each Y in Rn, again, we're talking about a B now, can be written uniquely in the form B equals Y hat plus Z, where Y hat is in W and Z is in W perp. So what this theorem is saying is we can decompose this vector B into the addition of two vectors, one in W, that's this vector here, B hat, which is in the column space of B, and then another vector that's perpendicular to our subspace W, in this case, perpendicular to the column space of A. So I'm just going to draw in this Z vector. So I've added my Z vector here, which is perpendicular to the column space of A and perpendicular in particular to B hat. And also, since I did write Z, since Z is equal to Y minus Y hat, I translated that Z is equal to B minus B hat. And of course, we know how to find B hat from our previous video, but remember, that's actually not what we're looking for. We're looking for the X that gets mapped to B hat. So we want to solve this equation here. We're going to call the X that gets mapped to B hat, we're going to call that X hat. So we're trying to find X hat such that AX hat equals B hat. This is our problem. So I cleared space out, but I believe this picture, along with this statement, summarizes what we've been discussing. And the statement that I have is we want to solve AX hat equals B hat, where B hat is the projection of the vector B onto the column space of A. Now, by the orthogonal decomposition theorem, which I have here for your reference, but it's the one we were just looking at in the previous slide, then Z, which is equal to B minus B hat, is orthogonal to B hat and also orthogonal to the column space of A. So if we find this X hat such that AX hat equals B hat, then Z is equal to B. Now we can substitute for B hat AX hat. So Z is equal to B minus AX hat is perpendicular to each column vector of A. That is, for any column vector of A, for example, A sub j. A sub j dot B minus AX hat will equal to 0. Or equivalently, to change from a dot product to a multiplication of two vectors, the dot U dot V is equal to U transpose V. So equivalently, this statement is AJ transpose times B minus AX hat is equal to 0. Since each A sub j transpose is a row of A transpose, right, because you get A transpose by taking the column vectors and transposing them and making those the rows. So since each A sub j transpose is a row of A of T, A transpose, then A transpose times B minus AX hat equals 0. And from this equation, we can multiply in the A transpose, and we get A transpose B minus A transpose AX hat equals 0, which implies that A transpose AX hat equals A transpose B. And this last equation here says that the least square solution to AX equals B satisfies A transpose AX hat equals A transpose B. And this equation is called the normal equations for AX equals B. Also, I have updated my graph to show that B is equal to B minus B hat. Also, we can write that as B minus AX hat, since B hat then is equal to AX hat. So finally, what we have is a way to solve for X hat. So X hat is equal to A transpose A inverse times A transpose B. I just multiplied both sides of this equation by A transpose inverse. To kind of quickly review what we just found, we wanted to solve this equation AX equals B, but A, the column space of A, doesn't reach B. In other words, this equation is inconsistent. It doesn't have solution. There's no X that you can multiply A to get B. So what we wanted to do is we wanted to find the best approximation. And by the best approximation theorem, this B hat, that A is in the column space of A, is the one that is the orthogonal projection of B onto the column space of A. So what ends up happening then is we want to find the X over here that gets mapped to this B hat, and we called that X hat. So we're solving the equation AX hat equals B hat, where B hat is the projection of B on the column space of A. To find this X hat, we use the orthogonal decomposition theorem. Essentially, we're going to use the fact that we have some orthogonality. We can dot it with something, set it equal to 0, and then solve for X. So by the orthogonal decomposition theorem, we have this, we can decompose this vector B into a B hat plus some other vector orthogonal to B hat. So Z equals B minus B hat is orthogonal to the column space of A. And again, that came from the orthogonal decomposition theorem. So if AX equals B hat, we can substitute AX hat in for this B hat and get Z equals B minus AX hat. And we'll know that that is now orthogonal to each column vector of A. That is, for every column vector of A, such as A sub j dotted with B minus AX hat will be equal to 0. Or equivalently, converting this dot product to a multiplication, we take A sub j transpose times B minus AX hat equals 0. And since each A sub j is a row of A transpose, this means that A transpose times, this is the matrix A transpose, times B minus AX hat will equal to 0. So now we have this matrix equation. We can solve that. We get the normal equations that A transpose AX hat equals A transpose B. And then we can solve for X, multiplying each side of this equation by A transpose inverse, and we get X hat is equal to A transpose A inverse times A transpose B. So this is the X over here, somewhere, this X is our X hat multiplied by A to give us B hat, which is the closest vector in the column space of A to the vector B. And I've also included this summary of how we derive the normal equations here on the overview sheet. We had mentioned that the normal equation always has a solution, so we can always find a closest value. And in fact, if there's a free variable, there may be multiple values, an infinite number of values that is the same distance from our original AX. So this theorem here gives us for criteria from when there is a unique least squared solution, exactly 1. And the theorem says let A be an m by n matrix, then the following statements are logically equivalent. 1, the equation AX equals B has a unique least squared solution for each B and Rn. 2, the columns of A are linearly independent. And 3, the matrix A transpose A is invertible. And when these statements are true, the least squared solution X hat is given by X hat is equal to A transpose A inverse A transpose B. And you will see this in both examples of multiple solutions and also unique solutions, and when A transpose A is not invertible in our examples. I have put my description of the least squares problem as well as the normal equations for AX equals B so that we can look at this example, find a least squared solution of the inconsistent system AX equals B when A is the 3 by 2 matrix with column vectors 4, 0, 1, 0, 2, 1, and B is the column vector 2, 0, 11. The first thing I just want to emphasize is the fact that this system of equations AX equals B is inconsistent. There's no solution. So if I take the augmented matrix of A and B and I row reduce, I eventually get an equation where 0 is equal to 21. So it's inconsistent. But I can find the closest approximation for an X that gets as close to B as possible. Using the normal equations, I see I need to transform this AX equals B equation into the normal equation. So I'm going to calculate A transpose A, which I have done here. I have A transpose times A, which gives me the 2 by 2 vector matrix with column vector 17, 1, 1, 5. And just a note, because A transpose and A, you're always going to get a square matrix. And then next on this side, I calculate A transpose B. So I have A transpose B, and I get the column vector 19, 11. Similarly, when you do A transpose B, you're always going to get a column vector. So I've transformed my original equation, AX equals this B, into this AX equals B. So I have my A is 17, 1, 1, 5. I have my X, and my new B is 19, 11. So I can solve this using row equations or row operations, or since A is invertible, I can use the other equation we had mentioned when we were deriving. We basically multiply both sides of our normal equation by A transpose A inverse. So X hat would be equal to A transpose A inverse times B. For this example, for whatever reason, I decided to use row operations. So for A inverse, I took my matrix A, I put it alongside my identity matrix. I did row reductions until A became the identity matrix, and then the identity matrix becomes the A inverse. So A inverse is 1 over AD4, 5, negative 1, negative 1, 17, which means X hat is equal to, gosh, I'm losing track of where I am. Oh, well, A inverse times B, right? We're trying to solve this equation now over, I couldn't find it. So we're trying to solve this equation, AX hat equals B hat. So that means that I can take the A inverse and multiply it times my B hat. So my A inverse is here, my B hat, my new B is 19, 11. So finally I get X hat is equal to 1, 2. For this next example, I went ahead and multiplied both sides of this equation, my normal equation, by A transpose inverse. So I get X hat equals A transpose A inverse times A transpose B. And this example is to find the least squares solution for AX equals B when A is this matrix here, 1, 2, 3, 4, 5, 6, 6 by 4 matrix with column vectors 1, 1, 1, 1, 1, 1. The next column vector is 1, 1, 0, 0, 0, 0. The third column vector is 0, 0, 1, 1, 0, 0. And the last column vector is 0, 0, 0, 0, 1, 1. B, the column vector B is negative 3, negative 1, 0, 2, 5, 1. And I'm going to start this problem by calculating A transpose times A. And again, you always get a square matrix when you multiply transpose times A. And my A transpose A is equal to the 4 by 4 with column vectors 6, 2, 2, 0, 2, 2, 0, 0, 2, 0, 2, 0, and 2, 0, 0, 2. My A transpose B vector, again, when you multiply A transpose B, you'll always get a column vector. And the column vector I get then is 4, negative 4, 2, 6. So I had given you this equation, but when I started to progress with this example, and I look at this matrix, it turns out that A transpose A, this matrix here, this first part of our augmented matrix, is not invertible. To confirm that, we can take the determinant of the matrix A transpose A, and we see that it's equal to negative 16, which is not equal to 0. By the invertible matrix theorem, a square matrix is invertible if and only if the determinant is equal to 0. So we can't use this formula here, and we're forced to do the row operations. And here are my row operations. So this matrix, augmented matrix here, is row equivalent to the 4 by 5 matrix with column vectors 1, 0, 0, 0, 0, 1, 0, 0, 0, negative 1, 1, 0, 1, 0, negative 1, 0, 3, negative 3, negative 2, 0. So this implies x4 is free, x3 is equal to minus 2 plus x4, x2 is equal to minus 3 plus x3, which is equal to minus 5 plus x4, and x1 is equal to 3 minus x4. So my general solution, my basis vectors, are 3 minus 5, minus 2, 0, and minus 1, 1, 1, 1 times x4. So that means this is my general solution. So because there's a free variable, there are many vectors that are equidistant from the vector b over where I can't even find our original b. Here, our original b. And we can choose x4 equal to 1. So one of the vectors, one of our closest least square solution will be x hat is equal to 2, minus 4, minus 1, and 1. So two things to take away is sometimes you do have an infinite number of solutions to the least squares problem, but you just, choose values for your free variable to get one of the solutions. The next example is given a and b from the previous example, determine the least squares error in the least squares error solution. So here we have the a and b from our last example. We found the solution x hat is equal to 1, 2. To find the error, we need to find the difference between b and b hat. So we'll start with finding b hat. So that's just a times x hat. So here we have our a matrix and our x hat, which is 1, 2. So our a times x hat, which is equal to b hat, is equal to the column vector 4, 4, 3. So b minus b hat, or b minus ax, where is b? Here's our b, 2, 0, 1, minus 4, 4, 3, is equal to minus 2, minus 4, 8. Finally, we're going to see what the magnitude of this error vector is. So the magnitude is equal to 2 squared minus 4 squared, 8 squared, square rooted, which is the square root of 84. So the least squares error is square root of 84. So for any x in Rn, the distance between b and any vector ax is at least square root of 84. I have two more problems to give you, but now that we have covered all the material in this video, I'm going to suggest after you hear the problem statement that you pause the video in order to try the problem yourself before looking at the solutions. The first problem is to find a least squares solution of ax equals b and compute the associated least squares error, where A is the 3 by 3 matrix with column vectors 1, 1, 1, negative 3, 5, 7, negative 3, 1, 2, and b is the vector 5, negative 3, negative 5. The second question is, what can you say about the least square solutions to ax equals b when b is orthogonal to the columns of A? Here's my first solution. I started by transforming to the normal equation. So I did my A transpose times A over here, and I get the 3 by 3 the 3 by 3 matrix with column vectors 3, 9, 0, 9, 83, 28, 0, 28, 4. I also did my A transpose B, and I get the column vector negative 3, negative 65, negative 28. So now I have my new equation, my new matrix equation, which is A transpose A times X equals A transpose B. So I had my augmented matrix of my A transpose A with B. I row reduce until I find that X3 is, well, I row reduce to the 3 by 4 matrix with column vectors 1, 0, 0, 3, 2, 0, 0, 1, 0, negative 1, negative 0, 0. So x3 is free, x2 is equal to 1/2 minus 2 minus x3, and x1 is equal to minus 2 plus 3/2 x3. So I wrote this out. x3 is free, so I chose, there's actually an infinite number of solutions because we have this free variable, but I chose x3 to be 0, so my x hat, my least squared solution, is going to be negative 2, negative 1, 0. I can then use my x hat to figure out what b hat is. So x hat, b hat is equal to a times x hat, so I have my a, which is my original matrix 3 by 3 with columns 1, 1, 1, minus 3, 5, 7, minus 3, 1, 2, and x hat again is my, this should be a minus 2, minus 1, 0. which is equal to, I wonder if I did this right. So I have minus 2 plus 3, minus 2 plus 3. I need to redo this. Actually, my error is over here. This x hat should be positive 2 minus 1, 0. So that my b now is a x hat. Putting in my correct x hat, is b hat is equal to 5, negative 3, negative 5. In this case, you can see that b equals b hat. And so there is no error in this problem. So actually b must be in the column space of A. The second question, what can you say about the least square solution to ax equals b when b is orthogonal to the columns of A? So if b is orthogonal to the columns of A, then the projection of b on the column vectors of A is 0. So the least square solution of ax equals b satisfies ax hat equals 0. To summarize what we have covered in this video, we looked at the least squared problem. So when we were given an equation ax equals b, it might be the case that we cannot solve this system of equations, but we still want to approximate an x that get us as close as possible to this value of b, this vector b. And in particular, we want an x such that b minus ax, in other words, the b we find minus ax is as small as possible. And that's how we define our least squared solution of ax equals b, that the distance between the b we find and ax is smaller than any other b minus ax prime for x prime in Rn. We noted that ax is in the column space of A, which we use later here in deriving this normal equations. So the solution to the least squares problem is given to us by this theorem, the normal equations for ax equals b, and it says the set of least squared solutions of ax equals b coincides with the non-empty set of solutions to the normal equation a transpose ax equals a transpose b. So what we've done is we've taken this inconsistent or possibly inconsistent equation ax equals b and transformed it into a system that definitely has solutions, and we transformed it into a transpose ax equals a transpose b. And I'm going to put a hat on these since these are not necessarily the original x and the original b. They're definitely not the original b. Or, well, they could be if this is consistent, but if it's not consistent, they're different. And then we did an example just to show you how this formula works. If A is the 3x2 matrix 4, 0, 1, 0, 2, 1, and B is the vector 2, 0, 1, this system of equations ax equals b is inconsistent. We cannot find an x that when we multiply a times x that gives us b. But we can use this formula here. We take A transpose A, which we did and got the 2x2 matrix 17, 1, 1, 5, and we took A transpose B, which we did over here and got the vector 19, 11. So this is our new system of equations, A transpose A x hat equals A transpose B hat. So we have our A transpose A x is equal to our new B, and then we can solve that. Certainly we can solve this doing row reduction with the augmented matrix, but I went ahead and calculated the inverse and solved it using the inverse. I have an outline of how we derived this normal equation, and since it's sort of detailed, I'm not going to review it a third time, but it is here for your reference. And then last, I noted that, or we had discussed before somewhere, if there is a free variable over here, if there's a free variable, the least squared solution may not be unique. This theorem here tells us exactly when the solution is unique. It's the criteria for unique least squared solution. In other words, the equation ax equals b has unique least squared solution for each b if and only if the columns of A are linearly independent, which is if and only if the matrix A transpose A is invertible. And when these statements are true, the least squared solution x hat is given by x hat is equal to A transpose A inverse A transpose B, which is exactly from this normal equation here. So that's it for this video. Thank you for watching.